All right, students, welcome to your AP Unit 6 problem walkthrough. We're not going to actually hit up any AP questions this round just because of where we are in our content, but we are going to walk through a few conceptual problems and then call it a day. So this first problem, question 4, is all about internal energy. Now remember, internal energy is the total energy in a system that is the sum of the work and the heat from the system's perspective. We can also put it in terms of ideal gas law through a rearrangement, but right now we have in this problem that a system released 64 kilojoules of energy as its internal energy increased by 43 kilojoules. Did the system do work on the surroundings or was work done on the system? So if we plug it into our internal energy equation where we say that Q, internal energy equals Q plus W, and here our Q would equal negative 64 kilojoules. And we say that our change in internal energy was increased, so positive 43 kilojoules. What is the value of the work? And so when we simplify this, we get that our work must equal positive 107 kilojoules, which means if work is positive, we would say then that work is done, okay, on the system by the surroundings, because in a sense, by having work done on the system, you have an energy input into the system, okay? So that's kind of just like really basic walkthrough. This tends not to be a huge topic in AP questions, but a topic that they do ask that you be familiar with according to the course manual. Okay, next walkthrough problem, question 8. Calculate the total energy change for the synthesis of diborane from its elements according to the equation using the following data. And this is a Hess's law question. So remember, Hess's law is one technique for calculating the total enthalpy of a reaction where we do some algebraic summation with smaller reactions to sum up to equal our overall reaction. And when we manipulate each individual reaction, we reflect that manipulation in the enthalpy value, as enthalpy is an extrinsic, that means amount dependent or mole amount dependent value. And it's also a dependent value in terms of which direction the reaction is going, forward or reverse. So what we have here is we are going to manipulate the following 4 reactions in such a way that we get the overall net reaction listed above. So what I'm going to do is I'm going to highlight the elements that I want. So I want 2 boron S. Okay, so I'm looking for boron S. So I find boron S. Do I see it anywhere else in the equations? No. And I also want H2. So I'm going to highlight every place that H2 is found. And I see it in 2 places. Okay, or actually, sorry, 1 place. And then I highlight, okay, finally B2H6. And I see it here. And that's it. So I see it in these 3 equations. Now, notice I do not find the B2H6 on the correct side of the equation. So automatically, I know I'm going to have to manipulate. Also notice that each of these particular chemical species that I want in my overall net reaction are part of 3 different reactions that also have their own products that we need to cancel out. Okay, so what I'm going to do is I'm going to start with writing 2B S plus 3 halves O2. And if you're like, whoa, that's not a whole number, totally right. There tends to be with tabularized data, sometimes we get non-whole coefficients because that particular energy value just goes with that particular coefficient ratio. Don't overthink it. It's just how tabular data works. Okay. And you know what, to save myself time, I'm not going to write in the states of matter right now because I just need to get the relevant chemical species isolated. And it goes to B2O3. And I'm going to keep that because I want in my net overall equation, I want 2BS on the reactant side, but I need to cancel out the B2O3. So I'm going to flip, okay, flip my reaction B and write it as B2O3 plus 3H2O goes to B2H6 plus 3O2. Okay, so notice something. That gets my B2H6 on the product side, which is what I wanted. And I still have my 2B on the reactant side, which is also what I wanted. But also notice that I cancel out my B2O3. All right. And to keep track, if I flip this reaction, that means that my enthalpy value for this particular reaction is the opposite. So it's going to be flipped itself. It's going to be positive 2035 kilojoules. And for the reaction above, since I just translated it down, it's actually going to stay the same enthalpy because I didn't do any type of math manipulation. Okay, so next step, H2 plus half O2 goes to H2O. That has my particular H2 that I want. And so I'm going to translate it down on the correct side. H2 plus a half O2 goes to H2O, which means that my enthalpy is going to stay the same as a negative 286 kilojoules. But what I am going to do now is I'm going to notice that my H2 is here. Oops, my H2 is where on the correct side where I want it to be in the overall net reaction, but not the correct coefficient. So now what I'm going to do is I'm going to multiply my entire reaction by 3. So I get a coefficient of, get a coefficient of 3 in front of everything. So now I'm going to say 3H2, 3 halves, and 3H2O. And if I multiply my entire reaction by 3, then my extrinsic amount dependent value of enthalpy is also going to be multiplied by 3 to reflect that. And then what I notice is when that occurs, my 3 H2Os get canceled because it's found on both the product and reactant when I sum. Okay. And finally, when I look at the final reaction, it's pretty much irrelevant, okay, to my equation of, you know what, actually, what did I make a mistake of? I made the mistake of, here's where the states of matter matter. I made the mistake of not noticing that these H2Os are in different states of matter. So this H2O is gas H2O, and this H2O is liquid H2O. Okay, so I actually can't cancel out those H2Os because they're not the same as reflected in the state of matter. So then I do need my final equation, and I look at my final equation, and it has H2O liquid on the reactant side goes to H2O gas. And because of that, now what I see is now I'm in a position where I can cancel out my H2Os from the sum overall net equation. But when I look at my H value and I look at my coefficients, okay, I should notice that I need to multiply by 3 in order to cancel out the H2O liquid and the H2O gas. So I take my value of 44 kilojoules and I multiply my whole reaction by 3, which means I multiply my molar enthalpy by 3 as well. And then what I see is that my H2O gas cancels out because it's found on the reactant in one equation and found on the product in the other. And my 3 H2O liquids cancel out. And now what I'm left with is 3 halves O2, 3 halves O2 on the reactant side, which is 1.5 plus 1.5, 3. O2s on the reactant side cancel out with my 3 O2 on the product. And then it becomes that my net reaction of 2B plus 3H2 goes to or produces B2H6 is indeed created. And so then what I do is I sum up the manipulated enthalpy values with respect to each subreaction, and I get that my total is the enthalpy for this reaction is 36 kilojoules. Okay, so that's kind of your walkthrough. And let's do one more problem. Question 11, okay. Use the following information along with tabular data to calculate the molar enthalpy of the formation of zinc sulfide. So with this equation, we're going to use the overall enthalpy of formation equation, which tells us that the enthalpy, the sum of the enthalpy of your products, or I guess you could say the enthalpy of formation for this reaction, the sum of your enthalpy of products, okay, under standard state conditions, minus the sum of your enthalpy of reactants, okay, and of course, times their molar coefficient, we can't forget that. Oops, is equal to the enthalpy of the overall reaction itself, enthalpy of formation. And if we have standard state indicated by this little not sign, you know that you're working with tabularized data that has been collected under specific conditions, particularly standard state conditions, I believe are, oh no, my brain is failing me. They are 1 atm pressure and room temperature. 1 atm pressure and room temperature conditions. All right. So what we do here is we would say, well, we're given our heat of formation total for this reaction, and we're trying to solve for zinc sulfide. Okay. And so we say that negative 878.2 kilojoules per mole is equal to the sum of the product tabularized data. So the products are zinc oxide and sulfur dioxide raised or multiplied by their coefficients. So if I look at a table, let's say I were to look at, in Safari, I just Googled tabular molar, let's see what I go, standard molar enthalpy of formation table is what I Googled. And I get this table and I look at my zinc oxide values for my product, and I see that it's negative 348 for the formation of zinc oxide. And for sulfur dioxide, I see it is negative 296.1. Other tables give 0.8, kind of depending on what book you use. So you will see even with tabular data, there's a little bit of contradiction at times or discrepancy, but for the most part, pretty similar. And so what I would say then is the sum of my products would be 2 times the molar enthalpy of formation value for zinc oxide, which was negative 348 kilojoules. And I'm just going to not write units in right now just to make it fit, plus the sum of my other product, which is sulfur dioxide, which was 296, well, 2 times negative 296.1 kilojoules per mole of forming sulfur dioxide times 2, because we have the coefficient of 2, subtracted we subtract from this product value the molar enthalpy of formation of our reactant species. Now, we're being asked to find, all right, zinc sulfide. So I'm going to say 2x and call this x. And it's going to be added to 3O2. Now, O2 is a diatomic molecule, and what we call it is a pure element. So for a diatomic pure element molecule, we actually find that the heat of formation is 0. Okay, 3 times 0. And that would be the reactant portion of our enthalpy of formation calculation. And what would happen is when we simplify this all out, we would get that our 2x value is equal to approximately negative 411. Okay, negative 411. Depending on your rounding, you might get a slightly different decimal. I know that the workbook answer key has a slightly different value for sulfur dioxide. So in the workbook, it says negative 411.4. I'm sure you're probably only like a 0.8 off. Okay. And then when you simplify and solve just for x, which is going to be equal to the molar enthalpy value heat of, or sorry, yeah, molar enthalpy value heat of formation for SO2. For SO2, we get that that is equal to approximately negative 205.7 kilojoules per mole. And that's your walkthrough. So it's just like a lot of math tracking, but for most of you guys are quite impressive in your math skills. So this should actually be quite a bit of relief for you in the AP chemistry curriculum. All right, really good job, you guys. Have a great one.